Nice. All right, so I will share my screen. And like a professional, I even had this pulled up already. Can everybody see the presentation? Preferably respond over mic. I only have the one monitor on my laptop, so I can't see chat. Oh my, it's yes, going. It's wait, that's not what I want. Is full screen the button I want? Okay, that's the button I want. So if someone can do me a favor, I'll try to like swipe over and check chat periodically. But if someone can make sure that any questions in chat that I'm not seeing get mentioned, that would be fantastic. Maybe Jade, since you're a host, if you don't mind doing that.
Yep, absolutely.
Okay. Great. So, programming for category theorists. So the idea behind this talk is going to be to talk about how sort of you could have come up with category theory only by thinking about how to write good programs. So some knowledge of programming is, I'm not going to assume a ton of familiarity with programming, but I am going to assume that you've at least seen some basic notions of writing programs. But we're also going to build up to it over time. So hopefully, hopefully it should be pretty approachable. So the plan was to write an entry-level talk. So I'm going to define pretty much everything as we go. If you've heard the word functor, you probably have the background for this. And like I said, the plan is to describe some deep connections between category theory on one hand and functional programming in particular on the other. For people new to the field, since I want this to be a very approachable talk, hopefully this will provide some justification as to why some of these categorical constructions are obvious or natural things to consider. And we'll also provide some intuition where you can leverage your experience with programming in order to understand these category theoretic constructions. Moreover, if you're already familiar with these category theoretic constructions, notably Cartesian closedness, maybe some familiarity with the notion of an internal logic, hopefully this will provide some new ways for you to see things that you're already used to, because I really am going to be attacking it from fundamentals as a programmer. And ideally, like I said, by the end of the talk, you'll see why some of these abstract things actually arise quite naturally in the context of programming. And if nothing else, this will give you an answer when people ask you, oh, why should I care about category theory? Which is a question I get asked disappointingly often. You know, homological algebra is a great answer, but if you're talking to like an engineer or something, you really need like a really down-to-earth, pragmatic answer for that kind of thing. And I think this provides a good justification for that. The one sad thing that I had to omit, which is a topic near and dear to my heart, is category theory and lambda calculus have a very intimate connection with proof theory. And in a certain sense, types can be viewed as theorems and programs can be viewed as their proofs. Unfortunately, I've had to omit that connection from the talk in the interest of keeping things approachable. But if people want to talk to me about that afterwards, please, please, please do. It's like one of my favorite branches of math, and I would love to talk about it. So let's go on. If you want to find these after the talk, I don't know if they're going to be posted on the category theory seminar page, but they'll definitely be on my website. Cool. So let's go ahead and get started then. So we'll start out with a toy programming language, which is a glorified calculator, basically. And over the course of the talk, we're going to add more and more features that a programmer might want. And we will see that the features we add end up being categorical in nature. So toy language Mach 1. Let's talk about what this means. This is called a grammar, and it defines the syntax of our programming language. So these T and F, T, F, and N are going to be things that we can write down sort of always. And then if we have two pre-existing expressions, we're going to recursively build up new expressions from these. So I think a definition by examples is probably the best way to talk about what I mean by this. So T for true is going to be an expression in our programming language. And that's because you can see T right here is a thing that we're allowed to write down. Similarly, we can write down false. We can also, for any natural number n, we can write down that number. So 5, for instance, falls into this n category. That's a thing we can write down. 5 plus 3 is a thing we can write down because we can write down 5, we can write down 3, And if I know how to write down two things, I'm allowed to write those things with a plus sign in between them. Similarly, I'm allowed to write down an if-then-else statement where E1, E2, and E3 are pre-existing things. So T I know how to write down, 4 I know how to write down, 2 plus 3 I know how to write down. So I can write down this if-then-else expression here. So here's another example where I can put this if-then-else, and then I can add 0 to it at the end. But there's an issue here, right? All of these we sort of know how to interpret if we interpret T as true, F as false, and N as the obvious number that we're considering. But we currently allow these kinds of bad expressions, not to pass value judgment on them. But so for instance, we can write down like false plus is a thing we can write down. And it's not clear how to assign meaning to this expression. We can write down like if 4, then true, else false. And these expressions aren't necessarily meaningful. And ideally, our programming language would figure out how to deal with these bad expressions. So that's an important question to worry about. So the first thing that we can do with these bad expressions is accept them and love them for who they are. They're just misunderstood. There's nothing I perhaps passed a value judgment too early. And if we just pick a convention to interpret these guys in, then we can carry on with our lives. So for instance, we can just say out of the void that false acts like 0 and true acts like 1. So if I see an expression false plus 4, I can interpret that as 0 plus 4. Or similarly, true plus 4 would be like 1 plus 4 is 5. Similarly, we can go the other way. We can coerce natural numbers into Booleans by saying that 0 is a falsy number and any positive number is a true-y number, right? And so this will allow us to expand what programs we can interpret. And this was a really popular approach back in the 90s and early 2000s. You see this in JavaScript, Python, Perl, PHP, basically any big scripting language. This is going to be the convention that they take. Unfortunately, or fortunately, from my perspective, it's falling out of favor because it leads to some really tricky to debug things, and it leads to a lot of counterintuitive behavior. This led to a rather famous meme in the programming language theory community, which is in JavaScript, you have this really weird chain of inequalities and equalities. So the empty set is equal to 0, and the string 0 is equal to 0, and a tab is equal to 0. But none of these things are equal to each other. And so, yeah, so JavaScript in particular, and really any scripting language with these quote unquote features, are going to have these sorts of counterintuitive behavior that makes it tricky to reason about programs. There's a whole website, javascriptwtf.com, which describes some of the counterintuitive behavior that comes from these things. I think there's one for Perl as well, but I don't know the actual website off the top of my head. OK, so answer 2 is these expressions are bad and they should feel bad. They aren't loved and we should get rid of them. And this is the current trend in programming language theory, is to find a way to exclude these expressions because they're really not worth considering. And the way that we exclude certain expressions is by adding what's called a type system to our language. So what is the notion of a type? Well, true plus 5 isn't meaningful because true is the wrong type of object, right? When we're adding two things, we would expect those two things to be numbers. And true is, among other things, not a number. So we add explicitly a notion of type to our language, and we only allow expressions where the types are what we expect. So for instance, if I'm adding two things together, both of those things should be numbers. So let's look at toy language Mach 2, where we're going to explicitly add a type system. So all of our expressions are the same, but now we also have these types tau that we're carrying along with our language. And we have this boldface B, the type of Booleans, and the type of naturals. And we also have to provide rules that tell us how our types interact. So I'm going to show these exactly once. The typing rules become progressively, they're never difficult to read. They just become long and unwieldy. It's kind of like taking derivatives in calculus, right? Where any individual rule is just kind of a sequence of really obvious steps, but taking the derivative of some really long expression is something that my students are actually taking a midterm on right now, and currently scares them. But let's see some typing rules, and then in the future, I'll just tell you the typing rules are the obvious things, and if you press me on it, I can show you details after the talk. So we write our rules like this. We say true has type Boolean, and we put a little line above it to indicate that with no assumptions, true has type bool. Similarly, with no assumptions, false has type bool, and with no assumptions, any number literal that you want to write down has type n. So these are sort of the base cases of our recursive definition. And then we add the inductive definitions as well, where if I know that E1 and E2 are numbers, then I'm allowed to say that E1 plus E2 has a number. So I'm not allowed to write this expression down unless I've already proven that E1 is a number and E2 is a number. Similarly, if E1 is a Boolean and E2 and E3 have any type, as long as they're the same, because an if then else expression works just as well if true then false else true, for instance, is a perfectly valid thing to write, as well as if true then 3 else 5. So as long as E2 and E3 have the same type, I'm allowed to assume, or I'm allowed to show that this if then else expression has that same type. And the only real condition is that E1 be a Boolean. And this is where the beautiful connection with proof theory lies. I think I've already been slipping into calling these things proofs or derivations a little bit. And that's because what we're really doing is we're proving some theorem. We're proving that E1 plus E2 has type natural. And if you make your type system rich enough, then this showing that a term has a certain type is equivalent to proving something about that type. And again, this is a very, very beautiful branch of mathematics. Please talk to me about it after the talk. Before I go on, are there any questions about type systems, how this stuff is happening? Is there anything in chat that I'm missing?
I have a question about
this
slide.
Yeah.
So in the box here, you have E colon equals a bunch of things with pipes between them.
Yes.
You also have tau equals B or N with pipes between them. But if I'm understanding it correctly, these pipes are different in the context of types versus the particular E, right? Because when we're talking about types, the pipe is really like a union or something.
Yeah, exactly. So these two things are currently separate. So we have a grammar for our types, and we have a grammar for expressions. And we want our types and our expressions to interact in a certain way. And the interaction between types and expressions is governed by these rules down here. And indeed, later on in the talk, currently tau is either B or N, but eventually this is going to be a recursive definition as well. Does that, I'm not fully sure I understood the question, but does that make some amount of sense?
Yeah, I guess so. Yeah, that makes sense.
If you ask it again, I could try to answer it again. Sorry.
Well, when we say tau equals B pipe N, like in set theory, I would think of this as a union, but I suppose it's not exactly a union in this case.
Yeah. So if you want, we're thinking about tau is you can think about tau as being we're thinking about this as the set. If you want, tau is the set containing B and containing N. We're not thinking about it as a disjoint union.
Okay.
Yeah.
I think it's like little e is like one of those expressions. Like e could be t, it could be f, etc. And similarly, tau could be b or could be n.
Exactly. Yep.
So you don't actually ever have the union of them.
Yeah. So you never have the union of them. Correct. All I'm doing is I'm defining what things I'm allowed to write down on the sheet of paper. And so I am asserting into existence the existence of the symbol B and the existence of the symbol N. And I'm saying these are symbols I'm allowed to write down. And indeed, here I am writing them down. But currently, even though this is supposed to be somewhat suggestive notation, this is purely notation right now. And it's not meaningful yet. Currently, it's just symbols on a page. And later, in categorical semantics, we're going to endow these symbols with meaning. Okay, so this is a pretty silly programming language because it's basically a calculator, right? It only knows about addition, and so it's not really doing a whole lot. We aren't really programming until we know how to define functions, right? Functions allow us to abstract common patterns that allow us to do the same thing to multiple inputs. And really, one of those functions is what we typically think of when we think of a program. So let's add syntax for programs, or for functions. So now we get to the infamous lambda calculus. The idea is we have all of our old expressions, but we're also going to allow our expressions to contain variables. So for instance, x plus 5 is now going to be a valid expression. And if b, then y plus 1, else 3 plus 2 is going to be a valid expression. And then once we have these expressions with variables in them, we're going to bind these variables. There's a Lord of the Rings joke to be made here, if I were cleverer. So lambda x of type n of x plus 5 is going to be a function which takes in some x, a natural, and spits out x plus 5. And similarly, lambda b of type bool, y of type n is the function which takes in a Boolean and then spits out this function. And this function takes in a natural and spits out whatever this happens to evaluate to. And we often want a function to be able to return multiple outputs. So think, for instance, about if you want to write some code which runs the Euclidean algorithm, right? You don't only want to output. So I have two numbers. I want to output that like one of them is some quotient plus some remainder for the division algorithm. Or I want to be able to not only do I want to show what the GCD of two numbers is, but I want to witness that I can write the GCD as a linear combination of the two things I'm GCDing. So I want to be able to return multiple things from my function. That's a very natural thing to do.
Right.
So we also at this, yes.
I have a question. So if you're adding this syntax, so is the lambda of blah, is that extending like all the previous things? Like, can we put lambdas into like the if else, right? Can we say if b, then y plus 1 else function?
So that would be expression.
Also, does the e defined to be equal to this true false thing? Does that list get extended by lambda blank?
Yes, you're skipping to the next slide.
Okay.
I'm going to write down explicitly what the grammar is on the next slide. Yeah. And so on this slide, I'm describing what we're going to add to the language, and I'm justifying why it's a natural thing to add from a programming perspective. And then on the next slide, we're going to actually formally write it down.
Okay. Sorry.
No, you're fine. You're fine. And so we also had syntax for tuples. So for instance, tuples allow us to pair two objects together or two expressions together so that we can return multiple values from a function. So for instance, this 5 true would be a tuple. And this is familiar in languages like basically every language. So here's toy language Mark 3. So we have all of the stuff that we used to have. But now, like Rahul just said, we're going to extend this with certain bonus features. So we have x of type tau is a variable, and we have to explicitly state what the type of our variable is. We also, given some expression e, we're going to allow ourselves to write down lambda x of type tau e is a new thing that we're allowing ourselves to write down. We also are going to allow ourselves to apply a function to an argument, right? So if E1 is some lambda expression and E2 is some input, then this allows me to actually evaluate this function on this input. And I'm also allowing tuples, so I can pair two programs together. And I can also get things out of a pair. So pi L would give me the left input, and pi R would give me the right input of my tuple. And now my types are also recursively defined, where I have types of Booleans, I have types of naturals, but I also have a type of functions. So for instance, I'll show some examples in a moment. But if I have some lambda term, it's going to have this function type. And if I have some product term, it's going to have some product type. So examples, lambda x goes to x, which is just the identity function, right? It takes in an x and then it spits out an x. that has type nat arrow nat. We can also apply two things. So if I have some lambda term, namely lambda x goes to x plus 3, and I have some input 4, then this will evaluate to 7, and that's a natural. And so similarly, this pair 5 true has type naturals times Boolean. And I can project out the right thing, and that will give me true of type Boolean. So yeah, again, I could write down these formal rules with a bunch of horizontal lines, and they tell you explicitly what the typing derivations are. But I'm going to not do that because they get complicated, and it's not really what I'm focusing on in this talk. Oh, here's one last example. So Rahul, you were asking if you could put lambda terms inside here, and yes, you can. So if you have some Boolean, you can have if b, then return this function, otherwise return this function. And that has type, well, it takes in a Boolean, and it spits out something of type natural to natural. So how do people feel about these examples? Hopefully it's somewhat clear. Let me check chat really quickly. It looks good. OK, so I'll go ahead and, oh, sorry.
So we've got E1 plus E2 it feels to me like that ought to be tied to like this lambda and then the application definition, but we have it as a primitive, and it just essentially gives the string E1 plus E2, right? Because we haven't endowed it with any understanding of any actual.
Correct. Correct. So I am allowing myself to write down the symbols E1 plus E2. And I think actually the next slide is I'm going to ask that exact question. Aha! Well done. So some pressing questions. This is cool and all, but I was promised category theory. And more importantly, how do we evaluate these programs? I know I'm allowed to write down this thing called plus, but how do we know what plus does, right? There's an obvious thing it should do, but we haven't talked about how we talk about what it does. So why can't 3 plus 5 evaluate to 15, say, or 35? You know, it's not obvious. So those are some very cute, astute questions, my Socratic dialogue partner, who happens to be Rahul. Good questions.
That actually wasn't exactly the question I was asking. My question was more on the typing of plus.
Yeah. So plus,
I could put any E.
Correct. So plus itself, because it's built into the language, does not properly have a type in this way. However, you could write down some expression like lambda x, lambda y, x plus y, which would have expression nat arrow, nat, for instance. But those are some slightly nitty-grittier details about the implementations of programming languages. And I think that's probably better asked after the talk.
OK, no worries.
Yeah, for sure. OK, so now we have this. So if you hang out with me long enough, you will hear me rant about syntax and semantics. I think this is arguably the most important duality in mathematics. And it is the observation that makes all of logic go. And the idea is that the syntax of some mathematical object tells me what things I'm allowed to write down about it, whereas the semantics tells me what the syntax means, right? So we've described the syntax of our programming language. We talked about what programs are allowable and what programs I'm allowed to write down, but we haven't said what the semantics are. We haven't said, given some program, how do I interpret it? How do I know what the program does and what it represents? So syntax and semantics part 2 enter the categories. And the important observation, due sort of initially to Levere and then later to Lambeck in this particular context, is that we can use categories to interpret our programming language. So the plan is that for every type that we have in our programming language, we're going to pick some object of our category. And then for every program of that type, we will have an element, where by an element, I mean in the category theoretic sense of an arrow from the terminal object. But that's, yeah, so I actually write that down. I mean an arrow from the terminal object to whatever object I've decided represents tau, corresponding to the program. But this is a kind of subtle point that isn't going to matter too much. You can, for a first thought about this, you can imagine elements as being like, we're working in the category of sets, and for every object, for every type, we pick some set to denote the programs of that type, and all of the expressions we can write down are going to actually be elements of this set. But category theoretically, it's slightly more natural to work with these arrows. So as we make our programming language more expressive, we're going to need progressively more structure on our categories in order to know that we can interpret everything we want our programming language to do. And so you have this natural back and forth between the complexity of the programming language and the structure on my category. And this is true in categorical logic more broadly. Again, if you want to talk about this, particularly in the first order categorical logic sense of like Mackay and Ray's, for instance, please talk to me about it. I think it's really, really cool. But let's see some examples. So let's only interpret our calculator programs. So let's not do lambda expressions for now. How would we interpret calculator programs in set? Well, step one, we pick a set for every type. Since we're starting out, let's take the obvious ones. Let's take the set of Booleans. We're going to be 0, 1. And the natural numbers are going to be, well, the natural numbers. Next, we pick an element for each value. So we again do the obvious thing because we're just starting out. You can come up with more exotic semantics later, where we're going to say true is going to correspond to this element 1, and false is going to correspond to this element 0. And obviously, n is going to correspond to the relevant element n in the natural numbers. Now, for each recursively defined term, we pick a function on the relevant set. So for instance, we have the symbol plus that we're allowed to use. And how do I interpret plus? Well, I interpret it as some function on sets from the product of the naturals to the naturals. So we can interpret this by any function we choose. But again, in the interest of starting out with obvious examples, we're going to interpret it as the actual addition function. Similarly, for if then else, we're going to have functions which take in these, a Boolean and two guys of type tau, and spit out some guy of type tau. And so notice if then else is kind of parameterized by tau. That's going to come up later. But for now, you can pick any old function for this if then else, and any old function for this if then else. And again, we're going to pick the obvious function. We know what if then else should do when we're given a Boolean and two naturals, so we're going to use that function. So now we can interpret programs just by composing these arrows. So for instance, if we start with the unit type, and then the unit type is naturally isomorphic to the product of the unit type with itself, and then we have an arrow from 1 times 1 to n times n, which sends this terminal object to 3, and this terminal object to 5, and then we can add them. And so all in all, this gives us an element. This gives us some function from 1 to the natural numbers. And so this composite up here picks out some element of the natural numbers, which corresponds to the program 3 plus 5. So up here we have the program 3 plus 5, and it spits out some number in the natural numbers. Down here, we have a different program, which is just 8. And the fact that this diagram commutes says exactly that these two programs are the same. That is, in our programming language, 5 plus 3 evaluates to 8. There's a subtle distinction here between the fact that these two programs are equal as programs versus a notion of evaluation. But that's something I'm going to gloss over, again, for the purposes of this talk. You can define what's called the dynamics of programming language, which tells you step by step how to actually evaluate it. But for now, we're going to work in this more abstract setting. But again, this is really how people reason about programming languages. Does this example make sense as to how we've now endowed all of our symbols with meaning, and we have shown that under this interpretation of the symbols, 5 plus 3 does in fact equal 8. How do people feel about that? Okay, people must feel good. So now we want to interpret these lambda terms. We want to be able to interpret some x of type tau e, right? Well, we want some, so this is a value, right? Functions are values. And so we want some object whose elements correspond to arrows, right? So for instance, if I have this expression x plus 5, then that expression is an arrow from the natural numbers to the natural numbers, which does the x plus 5-ness, right? And so if I want to write this as a term of my programming language, we need to be able to write this arrow as an element of some other object. Now, I'm going to rather suggestively use this notation, where I'm going to say we can find these arrows in bijection with elements of this form, where n to the n is going to, as usual, be the set of functions from the natural numbers to the natural numbers, still using set theoretic semantics. And there's this quick aside about how E itself is not an element. E is an arrow. And that's to do with the fact that E is not a closed term. It has some free variables floating around. And we only want to be able to actually evaluate programs with no free variables. That's a kind of subtle point. And if it didn't make sense, then ignore it. But more to the point, what categorical structure do we need in order to run this argument? We want to be able to say that this program, lambda x of type n goes to x plus 5, is some element of n to the n. So we need some categorical structure that allows us to write down things that look like n to the n, so that we can generalize from the case of the category set.
I have a question real quick.
Yeah.
So I'm a bit confused. Okay, so on the third bullet point at the end of it, you have x plus 5. So I was wondering if you could explain how we're supposed to think about constants, right? So if 5 is a constant, which really behaves like an arrow from 1 to n, right?
Yeah.
So does that mean that plus is a map from 2 arrows into n?
Yes.
So really, anytime you write n, it really means a map 1 to n, or is that
yeah. Yeah. If you want to be extra precise, then yes. When I say 5 is actually an arrow from the terminal object to n, where it picks out the element 5. And in non-separated Cartesian closed categories, that distinction becomes particularly important.
Well, but isn't that really like you're just saying 5 is an arrow from 1 to 5, but then 5 is itself an arrow from 1 to 5 to 5?
No. 5 is an arrow from 1 to the natural numbers.
Oh.
So in set, for instance, the terminal object is your favorite set with 1 point, right?
Yeah.
So a function from a set with 1 point to the natural numbers, the only thing it can do is send that 1 point somewhere. And I am identifying the number 5 in the set of the natural numbers with the function which sends this 1 point to the number 5, which is a very common thing to do categorically. But again, if that isn't something you're comfortable with, for now, we can just pretend, when I say element, this definition is what category theorists typically think of when they think of the word element. But in the category of sets, the two notions coincide. So you can really think of this as elements of a set, as far as intuition building goes. And it's only in more exotic Cartesian closed categories that you have to worry about this subtle distinction.
All right.
Yeah. So speaking of Cartesian closed categories, remember, we're trying to find some category which has the structure that allows us to interpret this notion of n to the n. And I will, for no apparent reason, recall the notion of a Cartesian closed category. A category is called Cartesian closed whenever it has all finite products. So given any two objects A and B, there's an object A times it behaves exactly like the Cartesian product in sets. There's some universal property which allows you to categorically describe what A times B is. But again, we're going to gloss over that for now. And one sort of important thing to note is that finite here includes 0, right? So if I product 0 things together, I get some terminal object 1, which is important, again, for defining elements formally. And I also have this notion of exponential object. That's the other thing that a Cartesian closed category has to have, where for any object A and B, I have this A to B, and the elements of B to the A correspond exactly to the arrows from A to B. So you can think about this as being a function type. Or you can think about this as being, yeah, the elements of this correspond exactly to functions. So this is exactly the structure that we need. If you're familiar with the notion of adjoint, then this exponential object is exactly the right adjoint to the finite product functor. But again, you don't need to know what that means in order to understand the fact that elements of exponential objects correspond to arrows, which is exactly the thing that we needed in order to interpret our lambda terms. And again, from this adjunction, or you can build it by hand if you're particularly dedicated, then this set of function objects comes equipped with an evaluation map, where if I have some function from A to B, and I have some guy in A, then I can evaluate that function at that point and get an element of B. If you want, this is the unit, co-unit. Evaluation things tend to be co-units. So this is probably the co-unit of the adjunction. But again, you can build it by hand if you want, just knowing that elements in here correspond exactly with maps from A to B. You can take this correspondence, get a thing from A to B, and then there's an obvious evaluation map, which takes an A to B, and evaluates. Okay, so rather remarkably, in the notion of just talking about programming languages, and wanting to know how to evaluate programs in a programming language, we found ourselves sort of inexorably drawn to this notion of Cartesian closedness, which is a really central theme in category theory. Cartesian closed categories are an extremely important class of categories. And so notice, just like set, we can now interpret our programs in any Cartesian closed category C. First, we pick objects B and N in our category to represent boldface B and boldface N. And then, using our Cartesian closedness, we know how to interpret product types because we know that C has product types. And we know how to interpret function types because we know that C has exponentials. Then we can pick elements from 1 to B and 1 to N corresponding to true, false, and every N in the natural numbers. And we pick these elements. And then lastly, we pick some arrows. So from N time, so this plus, that shouldn't be a boldface N. That should be one of these N's. Plus should be an arrow from N times N to N. And if then else should be an arrow like this in our category. So sort of all of the basic building blocks of our programming language, we interpret as various arrows in our category. And doing this, all of our programs, by a simple inductive argument, correspond to arrows in this category. And the programs with no free variables are exactly the elements. And so executing this program amounts to figuring out which element is named by the program. Okay, so this was a lot. And I added this slide last minute. So give me 1 second, and then we can go back to this. We can run this argument in reverse as well, where if I have my favorite Cartesian closed category C, we can build a programming language out of C. And how do we do that? Well, we add a type to my programming language for every object. We add a value, x of type A. This is a typo. That should say, this should be a function from 1 to A with an x above the line. I'm not sure what happened to my LaTeX there. But yeah, this should be a function from 1 to A with an x above the line. We can also add an expression, E sub f, for every arrow in here. And so in doing this, we have built a programming language who sort of, the semantics of this programming language are sort of very naturally done inside of this particular category C. And studying interpretations of this programming language in other Cartesian closed categories is a very powerful way of understanding the interaction between various Cartesian closed categories, in particular, the one you're interpreting it in and the one that you started with. And this programming language is called the internal logic of my Cartesian closed category. And for any category, you can build a Cartesian closed logic, or for any category, you can build an internal logic in a very similar way. And the kinds of programming languages that you get corresponds to the structure on C in a similar way, but dual to the way we discussed earlier. So that was a lot. So if you stuck with me through that, that was the peak in abstraction of the talk. And even if you didn't stick with me through that, the rest of the talk gets easier. So before we go on, are there any questions about particularly the last 2 or 3 slides? Because like I said, I know that that was a lot. And this is sort of the halfway point of the talk, and it's all down here, all downhill from here. Do people have questions about any of that?
My understanding of the internal logic is that the arrows sort of represent implications.
Okay.
And I guess I can sort of see the analogy where the arrows sort of represent programs instead. And I'm not sure I see how it's exactly the same.
Yeah, for sure. So remember at the start of the talk, I mentioned that there's this deep connection between programming language and proof theory that I was going to totally gloss over. Well, if you imagine you can find a program exactly when you're some notion of true, okay? And then if you have a program which transforms one type into another, so you have a function from A to B, and you know that A is true in some sense, then given a function from A to B, then I can turn the fact that A is true means I have some arrow from 1 to A, and I can compose that arrow with my function from A to B in order to get an arrow from 1 to B. And so that tells me that B is true in a certain sense. And so that's why these implications, that's why arrows in this category correspond to implications. And like you were saying, now constructing those arrows corresponds exactly to building a proof. And so witnessing that some arrow exists, you have to put an effort at some point. And witnessing that one of these arrows exists corresponds to making some proof. But I claim that witnessing some arrow exists is also the same thing as writing a program which describes that arrow. And it's in that sense that the internal logic in the sense of programming is the same as the internal logic as its original name in the sense of these implications of truth values. Again, this is a very, very deep topic. Please talk to me about it. I should have a small button that I wear everywhere that says talk to me about categorical logic. But I hope that provides a little bit more reasoning for some of the experts in the room as to why this notion of internal logic is the same as another definition of internal logic you may have seen.
Yes, thank you.
Yeah, for sure. Other questions about things before we move forward? Again, if you didn't understand this, that's fine. We're not really going to refer to categorical semantics again. It's just one of the big connections that I wanted to hit. Okay. So if there's no more questions, we'll go ahead and move on to polymorphism. So there's a natural question, if you'll excuse my pun, to be brought up in the sense that when we defined our semantics, we allowed ourselves to pick any old arrow, if then else sub tau, where we have some family of arrows parameterized by tau, right? And we allowed ourselves to pick any old arrow we wanted for tau. But obviously we want these arrows to have something to do with each other, right? Sure, we could just pick them arbitrarily, but they have the same syntax. And if we want the semantics and the syntax to be linked, if we want them to have a very tight connection between what we write down and what we interpret, we want these arrows to have something to do with each other, right? It would be very surprising if, let's say, if then else on the natural numbers, if I plug in something true, I get the first thing. But then randomly when I do this on Booleans, if I plug in something true, I get the second thing. That would be some counterintuitive behavior. And that's the kind of thing that we would like to outlaw in the same way we outlawed bad expressions earlier. But now we're outlawing things on the semantic side. Intuitively, we want to be able to give one interpretation that works uniformly for all types tau. Such an interpretation is called polymorphic, and it is an incredibly important and useful abstraction when programming. There's entire programming languages which are dedicated to trying to make polymorphism as useful as possible. So following Eilenberg and MacLean, before we can rigorously interpret polymorphism, we have to talk about functors. So A functor, really an endofunctor, but in the programming language community, it's traditional to just call them functors because we're almost never dealing with multiple categories, is a map F which assigns to every object of my category another object of that category. And to each arrow, if I have an arrow from A to B, that arrow should lift to an arrow from F of A to F of B in a way that's compatible with composition. So let's see some examples. There's the identity functor I, where I does nothing to the objects and does nothing to the arrows. There's also constant functors, right? So I can just ignore my input and always output this object X. And if I want everything to be compatible, I have no choice but to send every arrow to the identity arrow on X, which is guaranteed in the definition of a category. I can also have this functor, which I'm going to rather suggestively call if then else. And if then else takes in A and spits out this product X times A, which you might recognize as the left-hand side of if then else. And if then else of F is the map which, well, I have an X and I have two A's, I want to get an X and two B's. There's only one way to do that, and that's apply F to both of the A's that I'm carrying along in my data. And so that lets me lift a map from A to B to a map from X times A to X times B times B. So that's some examples of functors. But again, we're not really interested in functors for their own sake in this instance. We're interested in the idea of a natural transformation between functors. A natural transformation makes precise the idea that a construction is uniform in all the possible inputs. So we have something, in this case, if then else, and we would like to know that the construction doesn't depend on the choice of type tau. We want if then else should do the same thing no matter what tau I'm evaluating on. And it turns out that natural transformations are the correct setting in which to formalize this. And in fact, the whole field of category theory was created precisely because Eilenberg and MacLean wanted to take this notion of uniform construction and apply it to algebraic topology. So now we get to the definition. Given two functors f and g, a natural transformation from f to g is we have a collection of arrows theta sub a, which takes f of a to g of a, so that this diagram commutes for any way you instantiate the diagram, for any arrow f, for any objects a and b. So the idea is that if I perform my construction and then I modify whatever's inside of it by f, that's the same thing as modifying first and then performing my construction. So again, I think this is best done with an example. Let's see what happens with the intended interpretation of if then else. So let's say I start with true xy, right? Then if I apply f to this, my lifted version of f, then I get true f of x, f of y. And then if I do if then else, then I should get f of x because this is true, so I take the first guy. So I get f of x. If instead I first apply if then else, then this is true, so I get x. And then I apply f to x, and I get f of x. And notice that these two guys are equal. And so the fact that these two guys are equal, the square commutes, and this transformation is natural. Now you can imagine if I had picked some really bad definition of if then else, where let's say if then else A has the opposite convention as if then else B, then going the bottom way around this square, I would get f of x. But going the top way around this square, well, A has the opposite convention, so this would be y, and I would get f of y. And f of y is not equal to f of x in general. And so that is the sense in which natural transformations are able to detect the fact that this definition is uniform. If it weren't uniform, then I would be able to find one of these squares using an example of non-uniformity and show that this square doesn't commute. Okay, so the fact that this square does commute means that if then else is actually a natural transformation. It's a natural transformation from this type over here to, well, really the identity functor. So if then else if I want to talk about it being a uniform description, if I want to talk about it being polymorphic, then I actually have a natural transformation from this functor to this functor. Does that make sense in some capacity? This naturality, again, makes rigorous the idea that we really have one definition which works simultaneously for every type. I'll give people a second to parse that. But yeah. So.
Chris, I have a question.
For sure.
So in the example that you're giving, if then else has the sort of free types that are allowed there. They all, however, have to be the same, right? They're all indexed by A.
Yes.
Does it get significantly uglier if we were to say that those can all float relative to each other? Like, would this diagram become really gross?
So yes and no. If you want polymorphism of multiple variables at once, so let's say you had some magical if-then-else function where you didn't require this guy and this guy to be the same. But yeah, one, that wouldn't be well typed, which is why I'm stopping myself, because that's not a good example because it's impossible. But yes, you can have functors, or you can have functions which are polymorphic in multiple types at once. So you can have, for instance, the product type tau times sigma, or tau1 times tau2, is polymorphic in multiple variables. And yeah, there's categorical machinery for handling it. It is not much more complicated than this picture. I will say that. You have to be a little bit more careful, but it's basically a bunch of these pictures glued together. And you can pretty much consider each individual picture individually, so you're never looking at more than one square at once.
All right, dope, thanks.
Yeah. And kind of a fun fact, since I was saying this is maybe a new lens for some experts to view the world, this is how I think about natural transformations. When I see a natural transformation in the wild, I am interpreting it in my head, at least initially, as some sort of polymorphic function, because I have a lot of experience programming in programming languages with polymorphic functions, notably Haskell and SML. And so that makes sense to me, and I have a lot of intuition for what polymorphic functions have to act like. And so for me, and maybe for you as well, it's a good source of intuition for how natural transformations have to act. Okay.
I have a question on the previous slide.
Yeah.
So I'm a bit confused on the exact definition of a polymorphic function. So my understanding is we're supposed to have if then else parameterized by any type A, for which this diagram commutes. So is this supposed to be for like any functor between two categories?
So remember, for us, we're only going to be talking about endofunctors. We're only going to be talking about functors from some category to itself. Yeah. But if you're talking about natural transformations between functors which are allowed to change category, that is still in some sense polymorphic. But now the relationship is more tenuous and intuition-like than something that I can make formal. In this particular instance, you asked about the formal definition of polymorphism. The idea, again, is that I have to choose an arrow if then else for every possible output type. And I would like to know that I have one definition which simultaneously works for every possible output type. Namely, if true, then x else y should evaluate to x, and if false, then x else y should evaluate to y. And sort of that construction doesn't depend on the type of x and the type of y. And so that's what I mean by polymorphic. It is one function definition which simultaneously works for all types. And it turns out that polymorphism corresponds exactly to the notion of a natural transformation. And there's a really fun, I wasn't going to talk about this, but it's kind of on my mind now. There's a thing called theorems for free, which is a kind of fun buzzword in the programming language community, which is where you sort of, for free, get static guarantees about your code and how your code must execute just by knowing it's polymorphic. Because by knowing it's polymorphic, it corresponds to a natural transformation. And because it's a natural transformation, we have extra knowledge about how the code can run. how it interacts with lifting across functors, for instance. But yeah, did the first half of that answer your question with regards
Yeah,
to
that
what
makes sense.
Okay, cool. Okay, so there's one last example of category theory and functional programming being very close-knit friends. And we need to expand our toy language exactly one more time. So we're now going to add bonus types. We're going to add a new type of strings. And we're going to add a new type list of tau, where list of tau corresponds to a list of elements of type tau. So we now have this new way of adding strings to our language, where for any string, like hello, for instance, I think that's my first example. So for any string hello, in the same way we added a literal for every natural number, we now add a literal for every string. We also have this empty list of type, oh, that should say tau list. Whoops. So this should be empty list of type list of tau, not of type tau. We also have a way of consing two expressions together, which allows us to glue two shorter lists into a longer list. And we have this notion of fold, where fold lets us collapse a list in on itself. So we'll see some examples of that on the next slide. So this is the empty list, of course. If I have a value x, I can get a new list x cons x's. So for instance, the list of numbers 1, 2, 3, well, I have the empty list, and then I put a 3 at the front of the empty list. And then I put a 2 at the front of the list containing 3. And then I put a 1 at the front of the list containing 2 and 3. And so this is sort of the formal internal representation of what we're going to go ahead and write like this, because it's easier to read for humans. But this gives us a nice recursive or inductive definition of lists. And finally, we need some way of doing something with lists. You know, it's nice to be able to build them, but we should be able to use them for something. And so how do we cache out a previously constructed list? Well, if I have some function which combines guys of type tau, I have an initial value, x star of type tau, and I have some list x's, then I can fold this operation with my initial value along x's, and that just corresponds to right associating all of these x's. So for instance, if I were to fold the addition function with the initial value 0 on some list, that would correspond exactly to adding up all of the elements of my list. And if you don't understand exactly what fold does, that's okay. It's not going to be super relevant for us to the talk. It's just something that I felt bad not adding, because you need to be able to cache out lists somehow. Okay. And I could say some more category theoretic mumbo jumbo about this, in the sense that lists, yeah, if you want to hear some category theoretic mumbo jumbo about this, ask me after the talk. There's a good reason why this is done. Okay. So for instance, we can append two lists together by saying, well, the empty list append y's should be y's. And how do I append some x cons x's to y's? Well, I can recursively append x's to y's and then stick x in front of that, right? And that's exactly what we give here. We cons x onto the front of a recursive call to x's append y's. And we can implement this with this code, which I will leave you to verify at home. But the point is, this fold operation is already enough to write some non-trivial programs on lists. And while we're here, this is some stuff that I considered including in the talk but didn't. So if you're really excited about this stuff, can you see why this tau maps to list tau is a functor? And moreover, can you see why the empty list is actually a natural transformation from some constant functor to list, right? The empty list is some polymorphic thing. I told you polymorphic things are natural transformations. So it's some natural transformation from the constant terminal object functor to list. And maybe for the experts in the room, that's something to think about after the talk, because it's not immediately obvious. Okay, so now let's see a practical hypothetical. And this is going to be our last major connection between category theory and programming. Let's say you want to add some logs which make your program easier to debug. This is a very common trick in industry, is you have some flag to your program which lets you set a debug level, and you see various amounts of logs because, you know, Nothing makes things easier to debug quite like seeing a bunch of text on your screen saying what the program is thinking. So I have a bunch of functions of type tau1 to tau2, and I want to somehow modify these functions to make them keep track of a log file at the same time. And ideally, I shouldn't have to change my existing code base too much in order to do this, right? I should somehow be able to add logs to every individual function, and then since my program is just a composition of functions, everything should compose together nicely and keep track of all the logs for me. A good logging format that you consider might be this log of tau, which is going to be tau. And I'm going to also keep track of a list of strings, where that list of strings is my list of log files, or my log file. So again, we're keeping track of the same output that I used to return, but I also have a list of string representing the logs I've seen so far. And you might write some code like this. So here's some example code. Double with log should output x plus x, which doubles. And it should also say double the number. Yeah, and I've switched away from lambda notation. I only realized that now. But you could also write this double with log equals, and then lambda x of type n, and then this. So there's one major issue, and that's we've broken compositionality in doing this, right? Because if I have some function f from tau1 to log of tau2, and some function g from tau2 to log of tau3, I can't compose these functions anymore. So yeah, I've modified each individual function in my code base, but now I can't glue my functions together to actually do the interesting non-trivial task that I wanted to, because log of tau2 is not tau2. That's okay though. Again, we write our own special code to handle composition for us, and then everywhere in our code base, we replace the old composition with this new composition, or in a programming language like Haskell, it gets handled for you because composition is overloaded with type classes. And how do we do this? Well, intuitively, I have some function of type tau1 to log of tau2. I have some function which takes a tau2 and spits out a log of tau3. At the end of the day, I should get a log of tau3. Well, I take some t1 of type tau1, and I hit it with f, and I get a t2 and my first log file. Well, I can take out the t2, and I can hit that with g, and that gives me t3 and a second log file. And now I return t3, and I glue my log files together with the append function that we wrote earlier. And you can write this formally if you want to. Exercise, check that this is correct. But this is in our toy programming language implementing this idea. And we write this as f-fish-g. I don't know why we call it fish. I suppose it looks slightly like a fish, but that's how we would write this. This is obviously silly, but does anyone have questions about the idea behind how we are going to compose these two functions? Okay, so I guess we'll go ahead and move on. So the experienced category theorists are probably jumping up and down right now, screaming at the edge of their seats, because let's think about the data that we just described. Again, just purely trying to make a code base handle log files in a way that minimizes the amount of extra code you have to write. We have some functor, which I'll let you check that it's a functor, which takes tau to log of tau. And we have some fancy composition of arrows, where if I have, oh, this should say tau1 to log of tau2, I can compose these arrows. And that's exactly the data of Kleisli composition, which Kleisli composition tells you exactly how to compose arrows of this form in a category. And this tells us that our endofunctor log is actually a particularly special kind of functor. It's what's called a monad. And at this point, programming theorists in the room are screaming as well, because everything's a monad in Haskell, for instance. And again, this is in the same way that polymorphic functions are my first instinct for working with natural transformations. This notion of sort of data structures and data with some bonus information attached to it is my first source of intuition for working with more abstract monads in the rest of category theory. So if you're not comfy with monads, maybe learning a functional programming language and getting some intuition in this concrete case can help you go the rest of the way. This is how I learned category theory. And yeah, exactly what I said. They tend to act like data structures where you spruce up an object with some bonus structure. And at the end of the day, this is so cool because real people care about this, you know, like a lot of analysts, for instance, and other mathematicians who will not be named, they tend to get really upset at category theorists, and they say, oh, it's not useful, no one cares about it. When is any of this going to be applicable in the real world? Where, okay, if the real world is solving partial differential equations, maybe not. But if the real world is writing code for Facebook, which I would argue is almost more real world than PDEs, lots of real people do care about this machinery. So in the last 10 years, there's been a big push of software engineers getting interested in category theory for exactly this reason. And it's not just a niche thing either. If you go ahead and Google Monad tutorial, you'll see hundreds of tutorials in various levels of detail and various amounts of correctness, unfortunately, trying to explain monads to people, in particular software engineers. And again, if nothing else, hopefully this talk gave you a good response to what's the point of this abstract nonsense. And again, I think this is a good lens for newcomers in the field. I learned category theory and first got interested in category theory precisely because I was interested in programming. I love functional programming. I was a Haskell programmer. I have been a Haskell programmer for a long time. And trying to write good Haskell code forced me to learn a lot of these categorical ideas and encouraged me to learn a lot of these categorical ideas, which then, as a math major, I started seeing sort of all around me in my algebra classes, for instance. And I maintain that having these nice concrete computational examples are a really good way to gain intuition for a lot of these categorical notions. And it's not just, the rabbit hole doesn't stop here. Software engineers are interested in more than just monads, and they're interested in more than just sort of kind of surface level category theory. So here's some screenshots of some real examples in the world. So JavaScript monads made simple. So even JavaScript programmers, sort of the backbone of the internet, are interested in monads. And if you Google JavaScript monad tutorial, you'll find, again, hundreds of tutorials. Bartosz Milewski has an entire he has an entire book, Category Theory for Programmers. And there's articles and articles on the Haskell forums and Haskell Wiki talking about really intense category theory, understanding F-algebras being sort of just the basics of this, in my opinion, more advanced category theory. But the rabbit hole goes arbitrarily deep, particularly for Haskell programmers. And it's a little bit small over here, but this is called Haxel, which is actually Facebook's spam filter, is written in Haskell. And you can see haxel.core.monad, where sort of category theories and this notion of a Haxel monad, where Haxel is the name of the project. Haxel isn't a category theoretic word. But monadic programming is at the core of Facebook's spam filter. So it really is things that real people in the real world care about. And that's it. That's the talk. Thank you. Are there any extra questions? Okay. Actually, the timing ended up working out quite well on that. Okay. Questions about things. I'll stop sharing my screen now.
Oh, I have one question. So throughout this talk, so like you have expressions, but is there any law, like is it ever relevant to say that an expression exactly has one type, or are we allowed to have them have zero or multiple types?
Yeah, so every expression has exactly one type.
So what about if I say if whatever, then whatever else whatever, what is the type of that?
Yeah, so fair. So that will have the type of what the whatevers are, right? So if you say if true then 5 else 4, then that has type natural. And if you have if true then hello else hi, that has type string. If true then is it something that you can write down in the language?
There's some languages that actually do it differently than that, where you have like an expression type, which is weird.
So oh god, I have my old PL theory textbook in the other room that I can check, but I think it's PCF. All of the names of the various programming languages are muddled in my mind. But I think it's PCF, where you can have what's called higher order types. And higher order types allow you to explicitly express polymorphism as a first order thing in your language that you can talk about. And interpreting higher order types and categories is not something that I've actually thought about. So I'm not sure how you go about doing it, but it is something that people think about. And I'm sure there is a categorical semantics for it if you Google around.
Chris, I have a question.
Yeah,
so
for sure.
My background on this and my understanding of so I'm assuming similar to yours is that this is good for computer programming and that's cool. But you mentioned at one point that there's something about interpreting your program in another category. Can you touch on that a little bit? Because I don't think I understand the pure side of category theory enough to understand what that means.
Yeah, absolutely, absolutely. So this is sort of a generalization of the notion of a Levier theory, if you've heard of that. The idea is that to some category with structure, I can always associate its internal logic, which for me is a kind of programming language associated to the category. Now, given a programming language, we also know how to interpret it in a sufficiently structured category. And theorem, the programming language that you get from a category aligns precisely with the structure that that category has, right? So at the basic level, if you start with just a category with finite products and nothing else, then you get some sort of equational theory as your programming language. And then you can interpret this equational theory in other categories. In a way, the way doesn't matter, but in the same way that we interpreted programs in Cartesian closed categories, you can interpret equational theories in any category with finite products. And so if I have some category A, I can look at I can pretend it's a Levier theory. I can look at the programming language or the equational theory associated to that category. And then I can try interpreting that theory in some other category B. And what this does is it gives a kind of picture of a category A living inside the category B. And this gives you all kinds of nice theorems. For instance, this gives you the existence of certain left adjoints for free. This gives you, without the adjoint functor theorem, if you look at the equational theory of rings, you can interpret the equational theory of abelian groups in the theory of rings. And it turns out that this immediately provides you with a left adjoint from the theory of abelian groups to the theory of rings, which is cool. And you can do similar, albeit more complicated expressions, where if I have some Cartesian closed category C, I can look at its internal logic, which again is a programming language that I associate to that Cartesian closed category. Now, if I have some other Cartesian closed category D, I can say, okay, what do programs in my C language look like in D? And those will again correspond to Cartesian closed preserving functors from my category C to my category D. And this again gives me some picture of C living inside of D. And that gives me, just by reasoning about these programs, a way of reasoning about the interactions between C and D as Cartesian closed categories. So that was kind of high level and used some bigger words than I planned to, but hopefully that gives some idea of what I meant by that and why it's useful.
Sort of. So you're using the phrase programming language or program in this context in the style of like Curry-Howard isomorphism, not like, oh, let's do it in Haskell.
So yes, I am looking at Haskell as a particular programming language, and it corresponds to the Cartesian closed category Hask. And Hask actually has a bunch of other bonus features because Haskell is a very rich programming language. But for any Cartesian closed category C, you can look at a programming language, and by this I really do mean a programming language that you can evaluate code, which corresponds to doing function composition in C. And you can evaluate those programs in other Cartesian closed categories as well. So that's Yeah, that's what I mean. This would be better explained at a blackboard, unfortunately.
Yeah, no worries.
Yeah.
That,
But
that,
yeah,
that kind
talking
of scratches what I'm trying to get my head around.
Cool. There's a question in chat that I saw, the distinction between types and kinds. No, so the distinction between types and kinds is not what I meant by higher order types. What I meant is that, so if you want to be able to talk about if then else as a proper function, you can imagine it as a function which first takes in a type, tau, and then is a function of type Boolean goes to tau, goes to tau, goes to tau. So you are now having functions which can, in addition to taking elements as inputs, you have functions which can take types as inputs. And this is something that Haskell allows with its type class system. And it allows you to explicitly do certain things with polymorphism that you could not otherwise do. And I know a lot about for certain definitions of a lot, I know some things about what's called operational semantics of these programming languages, which is where instead of interpreting these programs in some category, you interpret these programs just as strings of symbols. And I am, in addition to giving you rules for what symbols I can write down, I give you rules for how to push these symbols around. And I view executing a program as pushing my symbols until I get to a thing where I can't push the symbols anymore. And this is how certain PL theorists, notably Bob Harper, talk about semantics of programming languages, because it makes it very clear how to implement the programming language. And so I took a class where we had to do a lot of that. And so I know about implementing programming languages with, for instance, higher order types in this sense, or higher order functions rather. But I'm slightly fuzzier on how you go about interpreting these things categorically. So I'll look into that after the talk, because I didn't realize I didn't know about that. So it would be a prop rather than a Levere theory. I mean, you get an algebraic functor from, okay, so wait. So you can interpret the theory of abelian groups in the theory of rings. So that gives you a functor from the Levere theory of abelian groups to the Levere theory of rings. But then you dualize and you get a functor going from the theory of rings to the theory of abelian groups, which is exactly the forgetful functor. But because every algebraic functor has an adjoint, that tells you that you also get some functor from abelian groups to rings, which is exactly do the direct product of all the n tensor products. So I really do think I meant Levere theory there. Although maybe I misspoke. Yeah, I'm not saying this as interpreting rings as monoids in abelian category. I'm talking about rings are themselves, well, commutative rings with one, obviously, are an equational theory as well. So they also have their own Levere theory. Yeah, other questions about things? That was a ton of information. Props to everyone for sticking through it.
I have a question.
Yeah.
I don't really have the question in my head yet, or exactly how I want to say it, but it's more geared towards like the application side. So my memory is kind of bad, but I think when, like in the beginning, when you were talking about tuples, you're also talking about like program functions. And I guess in like on the actual application side of things, are tuples used for like inputs and outputs of those, or no?
Yeah, so in the real world, people use tuples all the time.
Sure.
Yeah, and so I sort of justified tuples by saying you might want a function to return multiple things at once, right? So if you're running the Euclidean algorithm, for instance, you might not only want to return the GCD, but some witness to the fact that you can write the GCD as a linear combination of the guys you're GCDing. That's like what, the Chinese remainder theorem or something. But you can also, if you want to accept multiple inputs to a function, you can also accept a tuple.
So yeah. I guess then my question is more of like, so if you go to like really low level languages, like even like assembly code,
for sure,
tuples are very like not natural.
Right. Yeah.
A lot of pointers instead. So I guess I'm curious how tuples translate to more low level languages, because like in the end it really is just like single things that you kind of
for sure. So this is sort of a. Isn't there some diagram of like when you're at the bottom of the ocean, things are weird, and then you're at the top of the ocean, things are light. There's like a little gradient and like temperature changes. So there's a similar spectrum of high level to low level programming languages for sort of colloquially defined terms. And generally, high level programming languages are that because they give you features that we as humans like reasoning about, right? And so sort of the fact that programming language theory naturally gives rise to categorical notions, I would argue, and your argument sort of leans into this as well, that it's really because human thought naturally leads to categorical notions. And that's why these things show up everywhere, where wanting to abstract functions in this way by lambda terms, or wanting to solve a problem by taking the problem, splitting it up into little pieces, and then composing the solutions back together, right? These are just sort of the way that humans at a high level solve problems. And that's what category theory is good at describing. If you want like really close to the metal languages, then you have to deal with like physics and electricity. And unfortunately, these things, assembly code is not a particularly categorical language, though there are researchers at CMU who are working on what's called typed assembly, is an assembly language which is close to the metal and is based in some amount of category theory, less than something like Haskell, but still some, with the promise of being able to prove properties. I've mentioned this a couple of times now, that proof theory and type theory are very intimately related. And so if you have a strong enough type system, you can actually make it so that your code only compiles if certain things are true about your code. And so if you're writing some assembly code that you really want to know is correct, like if you're writing code that's going to take us to Mars or whatever, ideally you should prove that your code does what you think it does and it can't error and things. And so there's people at CMU and probably other places as well working in typed assembly, which is down to the metal assembly programming language with a strong type system that allows you to prove properties about your assembly code at compile time. So there are people doing what you're talking about. But yeah, the notion of tuple is not a primitive in assembly. So I can't say much about it in particular.
Yeah. Okay. No, that makes sense. A lot of times, yeah, models which are easier to versus what we actually.
Yeah. And this is sort of why compiling is nice, right? Is it lets you take some programming language that we know how to deal with, and you turn it into something that computers know how to deal with. The semantics of higher order type stuff is dependent type theory. Is that right? That's possibly right. That's where types are allowed to depend on values. I'm not sure if it's the other way around. Yeah, well, what does bad things mean? So bad things would be like if you write some code that like, I don't know, maybe you write some code and it accidentally segmentation faults, right? And the seg fault was unexpected, and then it makes the nuclear winter happen, right? Right, like you want to know that your code, isn't going to do things that you don't intend. And so you want to prove, for instance, maybe that your code always terminates. That's a good one to have in mind. Maybe you want to prove that your code, if you say that it doubles a number, it actually doubles a number. You want to know that your code doesn't accidentally cause a nuclear winter, for instance. lots of things like this. And at the absolute furthest right-hand side of the spectrum, as far as code that you can have a really, really strong type system, is something like homotopy type theory, or Lean, or Coq, or Agda, pick your favorites, dependently typed language here. And yeah, if you, at this far side of the thing, all of your programs terminate by default. So you can't actually write code that doesn't terminate theorem. So it's not Turing complete, which is rather interesting. But you also get these things where you can actually write down code that not only does it say, I'm going to double a number, but the code doubles the number and outputs a proof that the number was doubled and outputs a proof that it pinky promise will not cause a nuclear winter. And so all of these things are sort of baked into the type system, which is really, really cool. The downside is that it makes programming in the language really annoying, right? Because now, in addition to writing code that works, you have to write code that works and provides a proof of the fact that it works. And so these things tend not to be used in the wild, although Idris is trying its best to get this kind of code used in the wild. Yeah. Cool. Other questions about stuff? There's a lot of good content in chat, honestly. Is there a reason that it's a trend in PL theory to exclude bad expressions? For exactly this reason. You want to not allow bad things to happen. And so you want to, the sort of a very common thing that you hear functional programmers say is that invalid states should be inexpressible. So if you expect, for instance, so like if you're solving a Rubik's Cube, right? And you construct some data structure that encodes the state of a Rubik's Cube, if you're really careful about how you code it, you should, there are certain states which are unreachable, right? Like if you just rotate one corner, that's an unreachable state of a Rubik's Cube. You should make your data structure in such a way that that state isn't even something you can write down. So not only can you get there, but there's no way to write it down. So this is one less thing for you as a programmer to think about, because maybe some user gives you bunk data where if it can be written down, but you're just pretty sure you can't get there, then if somebody fucks up and you accidentally get there, then now your code, all of your proofs fail because your proofs were assuming that you couldn't get to this state. And so you want to, at a type system level, guarantee that this code is not possible. And those are things that PL theorists really care about. Yeah, that's super cool, Alice. And there's a really cool thing in that vein, which is called phantom typing, which is a fun buzzword for people interested in this to Google. Maybe you shouldn't have been programming for nuclear weapons in the first place. Yeah, same. Okay, so it is 5:30 at this point. I am happy to stick around and keep talking about this stuff because I love it. Do other people have questions about things? Everyone wants to feel free to.
This question is going to be fairly tangential. Because now off of what Alice said and what someone else said that led to you talking about assembly. Raymond, I think, mentioned. So we're dealing with a very abstract model of what like the programming language is and like what the reality, for lack of a better term, lives in is. But if you were to talk about like things quote unquote close to the metal, or with like this high security, low security data, and the fact that we know that like even if you have like encrypted, I don't remember the words, but like privileged hardware, you can still get information out of it by using side channels. How much can we like talk about in this sort of abstract way, a way that doesn't like obliterate all these concerns, right? Because like this talking about it in this highly abstract way seems to say, no, we never have to. I'm getting feedback. I don't know why.
Oh no, that might be me. My laptop every now and then just decides to give. I'll mute my mic and you talk and tell me if it fixes the problem.
Okay. So the thought that I'm having, and yeah, it's working now, is that if you lift to this like really abstract setting,